Let us summarize the information about the work done in taking a electric field from one point to another in the electric field is obtained from the quantities electric potential and electric potential energy. There are two terms. From A to B integral E dot dr is the line integral of electric field between this point A and B, and this shows the work done by the electric field in taking a unit positive charge from A to B. It does not depend on the path. If you take a circular path, E dot dr will be 0, integral. The work required to be done against the electric field to bring a unit positive charge again from infinite distance, say from infinite distance to the electric field, say some charge is there is electric field, so you're bringing it from infinity. It is called the, if you bring it here, say somewhere here, it is called the electric potential of that point. So electric potential at point P, that is Vp, is given by, from infinity to P you are bringing, say this point is P. This will be E dot dr. The unit is joule per coulomb, we call it as volt. The symbol V is J by C. The dimensional formula is M1 L2 T minus 3 A minus 1. Absolute value of this electric potential has no importance, but only the value or only the change is it is important. That is why we are interested in potential difference, not the potential. The work done or work required to be done against the electric field to bring a given charge, say some q, from infinite distance to given point in the electric field is called the electric potential energy of that charge at that point. So the energy, you can say the electric potential energy is given by, again this is infinity to P, you are bringing E dot dr, same like this, but when you multiply it by Q, so Q into V is the amount of work done against electric field from bringing infinity to P. The absolute value of electric potential energy has no importance, only the change is important here also. Electric potential at point P lying at some distance r for a given point charge q is Vp is given by kq by r. The electric potential at a point at a distance r from an electric dipole. Electric dipole is what? You have charge, equal charge separated by say some distance. So the electric potential when this r is, this 2a is the distance between them, when this r is quite bigger than 2a, so this electric potential is given by 1 by 4 pi epsilon naught. This is P dot r. P, this r is the unit vector, and r square. The potential on it axis V will be given by 1 by 4 pi epsilon naught P by r square. The potential at equator of dipole, that is equator, is 0, but at axis it will be this value. The electric potential at point r due to system of point charges q1, q2, qn situated say at r1, r2 and rn is V, which is I from 1 sigma summation kqi r minus ri. This I varies from 1 to n. This ri varies from 1 to n. The electric potential at r, point r, due to continuous charge distribution Vr is given by 1 by 4 pi epsilon naught. This is for whole volume. This is rho r d tau r minus r dash. And the electric potential due to spherical shell is given by 1 by 4 pi epsilon q by r. When this r is quite bigger than r, so V is, when r is less than or equal to r, V is given by r is 4 pi epsilon naught. This small r becomes capital R here. A surface on which the electric potential is equal at point, say this is a surface. All the points, the potential is same, and this surface is known as, this kind of surface is known as equipotential surface. And the direction of electric field is normal. This is normal to the equipotential surface. Okay, this is the direction of electric field. E equal to minus dV by dl. This gives the magnitude of electric field in the direction of dl. Very small distance. To find E from V, in general we can use E as del V by del x, del V by del y, del V by del s, I, j, k. This is the vector form. The direction of electric field is that in which rate of decrease of electric potential with distance is maximum, and this direction is always normal to the equipotential surface. The electrostatic potential energy of system of charges from q1 to qn, which is situated at r1 to rn, is given by sigma. We are adding I has to be less than j, k, qi, qj, ri, rj, where all ri, j are j minus ri. The electrostatic potential energy of electric dipole in an external electric field is given by U equal to minus E dot P, which is EP cos theta. This is a dot product. When a metallic conductor is placed in an external electric field, what happens? A stationary charge distribution is induced on the surface of the conductor. The resultant electric field inside the conductor will be zero. The net electric charge inside the conductor will be zero. The electric field at every point on the outer surface of conductor is locally normal to the surface, and electric potential everywhere inside the conductor will remain constant. If there is a cavity inside the conductor, say you have this conductor and there is a cavity, even when the conductor is placed in an external electric field, the electric field inside this conductor and also inside this cavity will always be zero. And this is known as electrostatic shielding. When electric charge is placed on the metallic conductor, not say it is a conductor, now the charge is placed here. The electric field everywhere inside the conductor will be zero. The charge is distributed only on the outer surface like this. The electric field on the surface is locally normal and is given by E equal to sigma by epsilon naught. This is n cap. If the charge is placed inside the cavity in the conductor, the electric field in region which is outside the cavity but inside the conductor will remain zero. A device formed by two conductors insulated from each other, this is known as a capacitor like this. Its capacitance C will be equal to Q by V will always be constant. The unit of C is Coulomb by volt, which is called as farad. Micro is 10 to the power minus 6, pico is 10 to the power minus 12, nano is 10 to the power minus 9. The capacitance of parallel plate capacitor is given by C equal to epsilon naught A by D. The effective capacitance in series 1 by C will be 1 by C1 plus 1 by C2 plus 1 by C3. The effective capacitance in parallel will be given by C equal to C1 plus C2 plus C3. The energy stored in the capacitor Q is given by Q square by 2C. These are three equivalent expression. CV square by 2 and VQ by 2. And the energy density, that is energy per unit volume is given by 1 by 2 epsilon naught E square. E is the electric field here. When a dielectric is placed in an external electric field, say E0, polarization of dielectric will occur due to electric induction. So the electric field produced by these induced charges in the direction opposite to the direction of external electric field. So the resultant electric field E inside the dielectric will be less than the external electric field E0. The dipole moment produced per unit volume is called the intensity of polarization, or we can just say it as a polarization. So it is given by sigma B. This is B is for bound. This polarization is directly proportional to electric field. So P can be written as epsilon naught XE into E. This XE is called the electric susceptibility of the dielectric medium, and epsilon 1 plus XE, this is called the permittivity E, or epsilon, sorry, of the dielectric medium. Epsilon by epsilon naught is called the relative permittivity of that medium, and this is also known as K, which is called as dielectric constant. So epsilon by epsilon 0 can be written as epsilon R, this is subscript R, equal to K. K is 1 plus XE, E is equal to E naught by K. Dielectric, the electric field reduces to, if you see here, it is just reduced by 1 by kth part. D is equal to epsilon naught E plus P. This is called the dielectric displacement. Gauss law, in the presence of dielectric, can be written as, this is integral D dot ds equal to Q. Q is only the net free charge. When there is air or vacuum between the plates of parallel plate capacitor, the capacitance, this which is C equal to epsilon naught A by D, is the value, is the expression. Now on placing the medium of dielectric constant, say K, the capacitance C dash will be simply multiplication of this K with C. So the capacitance becomes K times due to the presence of a dielectric. Van de Graaff generator, with the help of Van de Graaff generator, a potential difference of very high value, few million volts, can be established.